Hey everybody, great to see you again. Mr. Smith here. What I'm going to do in this slide deck is to give you two really basic, really important math skills that you're going to need to be able to deal with vectors in two dimensions. So vectors in two dimensions, we've already done plenty with vectors in one dimension. So if you saw somebody move 50 meters to the west, that was a vector because it had a distance and a direction. So what we're going to do is talk about people doing two things at the same time. So here's an example of people doing two things at the same time. No, let me back up. This isn't about playing video games in class because everybody knows you can't do those two things successfully at one time. You either pay attention to the game or you pay attention to class. If you're paying attention to both, your game stinks because you're bad at it and you're not getting anything out of class. So let's go and talk about the actual cool example here, which is the physics. So the physics here shows this guy, or our wide receiver, running maybe to the west at, make up a speed, 8 meters per second or something like that, okay? That's the kind of vector we were talking about. He's moving in one direction at a time. Well, here's the thing. What we are going to talk about is this motion right here where he turns and runs a slant. And when he does that, you can see that he starts to run across the field as well as still down the field. So here's the part, I just drew a little dotted line to represent a triangle that I could make. This is a leg of a triangle. Check this out. He continues to run a little bit down the field and then runs across the field more. You can tell by the angle of this that he's running more down this way than he is this way, right? Okay. So in dealing with two motions at the same time, there are going to be situations where you want to take motions that are perpendicular and add them together to come up with this answer here, this compound thing called a resultant. That's what we're going to talk about in this slide deck. The other thing that we're going to talk about when we get down when we move on from here is how to take this vector right here and break it up into two motions at the same time. So before we do any of that stuff, what I want to do is do a quick review of a really important trig concept, and that's the coordinate plane. Okay, so the coordinate plane, if you've done any trig at all, you know we have our xy axis and that we have quadrants. So quadrant 1, quadrant 2, quadrant 3, quadrant 4. Now, I want everybody to know, and if you don't know, I want you to write it down, that these quadrants all are connected to angles. So 0 degrees points out this way to the east. And what we do when we think about the quadrants is we rotate or spin counterclockwise. And whenever we hit one of these cardinal axes, we're on some multiple of 90 degrees. So straight up north is 90 degrees. So the first quadrant's everything from 0 to 90. The second quadrant is every angle between 90 and 180. So 180 is out here, also known as west. The next one, the third quadrant, goes from 180 to 270, also known as south. And then the fourth quadrant is all this. It's just everything from 270 to get us back to 0 or 360. Okay, so you're going to see me use these numbers and make a couple of points about how to draw triangles right now. So let's go check out a few of these examples. First one, they're going to ask us to draw a vector that's going 10 meters at 65 degrees. So that when I see 65 degrees, what I recognize is that's in the first quadrant. So here's 0, here's 90. The first piece of advice I have for you is when you draw a vector, make sure that you start it at the coordinate hub. That's the origin of the coordinate system. The second hint that I want to give you is make your picture count for something. There are a lot of guys who do garbage pictures where every triangle is a 45, 45, 90, regardless of what axis it's in or what quadrant it's in. And it's a good way to cause mistakes to happen. So it's not a hard topic if you pay attention to a couple little details. So here's one of them. 65 is more than 45. So I'm going to want to draw a line that starts at the hub and scooches a little bit more towards 90 than it does towards 0. And that's going to be my 65-degree angle. Okay? A third little tidbit to keep in the back of your mind is you're going to want to be good at thinking of what's this mystery angle. That kind of logic where you think intuitively about If this is 65 and from here all the way up to this vertical is 90, this little angle right here must be 90 minus 65, right? And that's not hard to do. It's 25. There's all kinds of situations where it's going to be useful for you to be able to be quick and be able to do those things in your head. Okay? So let's check out this next one. 10 meters at 295 degrees. So we're going to think about our axes. Quadrant 1 is 0 to 90. 2 brings us up to 180. So we're past 280 to 180. Quadrant 3 brings us up to 270. So we're actually in the fourth quadrant with this guy. Okay? Here's what I do. I spin up to 270, and then I use the kind of thinking I was just doing. How much more than 270 is 290? Well, it's 25 degrees more. So I just draw a little bit further, and I draw my hub, the tail of the arrow at the origin, draw the arrow facing down this way, and now I know that the interior angle right there is 25 degrees, and that's going to really help me out when I get to solving these. Okay? Third one, let's go check out 135 degrees. So 0 to 90 is the first quadrant. So, well, this guy is more than 90 and less than 180. So let's go think about how much more. This is where that logic works again. Here's 90. To get to 135, I go 135 minus 90. And that's how much farther than 90 I have to go. Well, that actually is a good situation where I want to do a 45, 45, 90, because that's actually what the triangle is, okay? So you would notice, if you're paying attention, that I could have gone to 180 and backed off by 45 and still ended up with the same line right here, okay? So anyway, we'll use that kind of logic plenty, and you'll get lots of practice at it. But let's go jump on an actual example of adding vectors, and I'll show you the rules for how you do that. So in this example, what I'm going to ask you to do is to stop the slide right here, jot down these rules, and you're going to see us use these rules over and over again. Some of them are hard and fast math rules, some of them are just suggestions from me. But what I'm going to do is dive right in on this example, assuming that you did that and that you got these already written down. So you walk 100 meters north and then 40 meters west. This is how you add vectors. So we've got the first one, the long one, I draw first, and I'm going to borrow this part of the coordinate axis and just put a hat on it. And what that represents is the 100 meters north. So it starts here and then works its way straight up to represent north. And I'm going to put the number 100 meters on it. Then out of the tip of that, we draw the tail of the second arrow as though these were both one-way streets heading away from my house. So here's 40 meters right here. And the resultant, the answer vector, is going to be this one right here. And that is going to represent the actual distance and angle that I am from where I started. Okay, so let's go ahead and blow this up a little bit and show you in a bigger format how to solve this thing. So to solve this vector addition problem, the first thing I'm going to do is Pythagorean theorem, which is going to let me get the length of the hypotenuse right here. So I know from Pythagorean theorem that the resultant squared equals 40 squared plus 100 squared, and I can just go ahead and solve that on my calculator by plugging it in like so. And when I pull the trigger on that thing, I get 107.7. So do me a favor and keep a decimal point. The second thing I'm going to do is to figure out the interior angle right here. So what I'm going to do is to call that angle theta. My personal favorite is to always use the tangent to solve for these, just because there's no rounding involved. The sine and cosine are going to use this hypotenuse, and that's fine. You can do it as long as you show your work. But I'm going to use tangent of theta equals opposite over adjacent. So we know that opposite is 40, adjacent here is 100, and that means if I use my inverse trig function, the angle theta is going to equal tan to the minus 1, or the inverse tangent of 40, over 100. And when I pull the trigger on that in my calculator, that gives me 21.8 degrees. Now you're almost home free with the answer. The answer is going to be 107.7 meters at, and it's not going to be 21.8 degrees, because 21.8 degrees would be a low angle right over here in the first quadrant, right? What I have to remember is that the answer angle is always going to be where the resultant is. So starting from 0, I go 90 and then 21.8 more. So this answer angle is going to be 90 plus 21.8. So 90 plus 21.8 gives me 111.8 degrees, and that is the total answer. Okay, so real quick, 2 more examples here, and let's go ahead and finish it up. 40 meters south, 90 meters west. You're going to see for reasons why I always draw the long one first, but I'm going to just do it. So 90 meters west, I'm going to put the 90 meters on the top because I know my next shot is going to be down this way. That's my short one that I draw second. The answer, of course, is going to start from the hub and cut all the way across to the answer. So these are like one-way streets again. And the resultant, or the answer, is going to be the way a crow would fly from home to where I ended up. So same steps as before. The resultant here is going to equal the square root of the other 2 sides squared. And this one turns out to be 98.5. So that's my 98.5 meters. And then I'm going to go ahead and get an angle on the inside right here. So angle theta is equal to tangent to the minus 1 of opposite over adjacent of 40 over 90. And that turns out to equal, let's go ahead and get it, 24 degrees. And then there's finally the business of getting the total answer. The answer here is going to be 98.5 meters at, and now I have to think about quadrants. 0 is straight out this way, 90 is here, 180 is over this way to the west. I can see now that the answer is going to go all the way through all of these angles, and it's going to end up pointing right there along the resultant line. That's 180 plus 24. So the angle is going to finally be 204 degrees. Okay, that's it. Let's go ahead and check out one last one if you want to. It's a bonus question, but if you're working along with me and you're getting them right, great, you're good to go. Final example, I'm going to do 75 meters south and then 40 meters to the east. So since you're doing a little bonus work right here, 75 meters to the south, there's a real reason why I always draw the long ones first. It makes the diagrams a lot easier and it makes the tangent predictable. If you draw the long one first, then you always have a small angle on the inside of your triangle, and that makes it easier to work. It makes the trig consistent, and it also makes it easier to think about the compass when it gets down to it. Okay, so 40 meters rather is going to branch to the east out of that, and I've got this kind of 4th quadrant deal going on right there. And so as we did before, r is going to equal just the hypotenuse, so 40 squared plus 75 squared, and that's going to come out to equal 85, like on the nose. Step 2, you want to identify this angle in here, Greek letter theta. So theta equals, to me, at least tangent to the minus 1 of 40 over 75. So you can certainly use your other trig functions if you like to, but I like the tangent. And that comes up with 28 degrees. So my final answer is going to end up being 85 meters at, and let's think it through now, 0, 90, 270, 270 straight down, right? Plus 28, 270 plus 28 looks like 298 degrees every day of the week, and that's how you do it. Okay, so adding vectors, 2 things at the same time. So bring questions to class. Looking forward to seeing you then. Have a great day. Take care. Bye-bye.